Today we'll introduce the unit circle and we'll also do a refresher of common reference angles. So let's start off with the equation of a circle centered at the origin. So it starts at 0, 0. We take a point P with an x value and a y value, and we use that to represent the point at the end of the radius. So this segment has a length of r, and we know, due to Pythagorean theorem, that x squared plus y squared is equal to r squared. So this is kind of our general formula for all of those points. We can include negative values of x and y on the coordinate plane and the equation will still be valid. However, we always say that r, or our radius, has a positive value. Now we're going to look specifically at the unit circle, and the unit circle has a radius of 1. So its equation is x squared plus y squared equals 1. Let's just take a look at a couple of examples and then we'll come back to the angles afterwards. So if we just want to write out an equation for a circle with a center at the origin and a radius of 5, we will use x squared plus y squared equals r squared, where r is 5, so 5 squared. And multiplying that out, it would have an equation of x squared plus y squared equals 25. Going in the opposite direction, if we have an equation, for example, x squared plus y squared equals 7.29, we know that r squared is equal to 7.29. So if we wanted to find the radius of that circle, the radius is equal to the square root of 7.29, and when we calculate that in this case, the radius is equal to 2.7. And that's the basic idea for the equation of a circle. Now, for the unit circle in particular, really what this just means is our radius is 1. So when we find our x value and our y value, and we do x squared plus y squared, it should be equal to 1. For any angle, you can extend the terminal arm, so it could have a longer terminal arm of r, or on the unit circle it would have a shorter terminal arm of 1. And that essentially is just a way of scaling down our triangle so that the radius is 1. It doesn't change the value of the angle, we're just taking a smaller version of the triangle. Now, what we're going to do with this to start with is a couple of things. The first thing is, if we know one of the points or part of the coordinate, for example, if we know the y value, we can find the x value for any point on the unit circle, because knowing that we have the unit circle, we're kind of given the extra piece of information that we know the radius. So for example, we say that x squared plus y squared is equal to r squared. We want to find the values of x for all points on the unit circle that have this y coordinate root 3 over 5. Let's draw ourselves a unit circle. It doesn't have to be perfect, but maybe we'll do the circle first and then put in the x and y axis. So, oops, try and center it to the best of your ability. There's our unit circle. And I'm going to just grab that for later too. So in this case, we want to find the points on the unit circle where the y coordinate is root 3 over 5. Let's say that's somewhere around here, a height of root 3 over 5, given that we know that up there is 1. Now, if there is one point there with that height, there's actually another point over here with the same height, just with a different x value. So let's draw in a radius of 1, and we have a y value of root 3 over 5. We're trying to find x. There is one point on quadrant 1 that does that. There is also another point on quadrant 2. Same radius of 1, same y value of root 3 over 5. The difference in this just comes down to the fact that whatever our x value is, it's going to be negative instead of positive. I'll just write in negative x. So we can solve this using the equation, given that we know y and r, and we're just finding x. And we know that we will have two possible solutions for x, the positive and the negative. So let's pop this in. Our radius is 1, so we can say 1 squared is equal to x squared plus y squared, where y is root 3 over 5. And we do want to try and keep an exact value on this, so we're going to multiply this out ourselves, not get a decimal in a calculator. So 1 is equal to x squared plus 3 over 25. X squared is equal to 22 over 25. Now we actually want to find x, so we're going to take the square root. And we are going to take both the positive and negative square root because, as we said, there are two possible x values. So x is going to be equal to plus or minus the square root of 22, and in the denominator, the square root of 25 is just 5. So our exact values for x are positive root 22 over 5 and negative root 22 over 5. That means that we have a coordinate, I'll just write p here, where your x value is plus or minus root 22 over 5, and your y value is root 3 over 5. Okay, let's take a look at a second example like that. We want to determine the values of y for all points on the unit circle if this time we know x is equal to 0.7, and the angle in standard position terminates in quadrant 4. So we know we have a positive x value of 0.7, but knowing that the angle terminates in quadrant 4, we actually only have one x value. If there was no limit on the quadrants, you could have another x value that was positive in quadrant 1, but we are limited to quadrant 4. So let's sketch in a point here. We know that our radius is 1 on the unit circle, our x value is positive 0.7, and we need to find our y value. Now in this case, knowing that we are in quadrant 4, what do we know about y? We know that y is negative. So when we solve for y, we need to take the negative value for y. And again, we'll start with x squared plus y squared equals r squared. On the unit circle, r is 1, so we have 0.7 squared plus y squared equals 1. Y squared equals 1 minus 0.49 for the 0.7 squared. So y is equal to, we take the square root, but we specifically take the negative square root of 0.51. That is a slightly more exact answer, but that one is not really fully simplified because we have a decimal inside a radical. If we wanted a more practical answer, let's just go to 2 decimals. This is negative 0.71. Feel okay? Great. Now, before we go ahead, let's come back to this little piece here. And just notice a little bit of notation here. Points on the unit circle can also be named by an angle. So instead of saying p x comma y, which gives you an x value and a y value of the coordinate, you can also use p theta, where theta is the angle in standard position. The reason for that is you are only going to have a point where r is equal to 1 because we're on the unit circle. So your x squared plus y squared will always equal 1, what we had over here. And because of that, that kind of gives us another way of identifying the point. So if you know the angle, you should be able to find an x and y value because there is only one x and y value for a point with that angle on the unit circle. All right, let's go ahead and let's just do a little refresher of our special triangles. Let's look at them in their original form first. So this is how we used our special triangles last year. We had a 1, 1, root 2 triangle with 45-degree angles. We had a 1, root 3, 2 triangle with 30 and 60 degrees. So those are kind of our 3 special angles, 30 degrees, 45 degrees, 60 degrees, where we can calculate all of our trig ratios with an exact value without using a calculator. We can do the same thing in radians. So just as a little refresher, 45 degrees is pi over 4. 30 degrees is pi over 6, and 60 degrees is pi over 3. Now, these are great for giving us trig ratios. It's a little inconvenient for the unit circle because if you think about it, when you draw the triangle, this one is going to have a radius of root 2. This one is going to have a radius of 2. So what we do is we can actually scale down these triangles and use a similar triangle with shorter side lengths. So for example, if right now our radius is root 2 and we want our radius to be 1, what if we divide by root 2? So I'm just going to temporarily write it in and then we'll go to the next triangle. Divide by root 2, that would be 1. Divide by root 2, divide by root 2. If we rationalize this, which we really should, it's root 2 over 2. So we also have a smaller special triangle with the same angles. Pi over 4, pi over 4, root 2 over 2, root 2 over 2, and a radius of 1. That allows us to now draw the triangle so that our point on the terminal arm will have a radius of 1 and it will be on the unit circle. If you take a look below, that is the filled in triangle that you have. Just keep in mind, if you're working in radians, this is pi over 4. We can do something similar for our other triangle. So for our other triangle, we originally had a radius of 2. What if we just divide all of our side lengths by 2? If we do that, we now have a similar triangle with the same angles where our sides are 1/2, root 3 over 2, and a radius of 1. Okay. These aren't necessarily new versions of the triangle you need to memorize if you're okay with scaling down. So for example, if you have a radius of 2, divide by 2. If you have a radius of root 2, notice how we just divided by root 2 to make it a radius of 1. We can use these if we are given an angle and we want to find a point on the unit circle that is on the terminal arm of the angle. Let's take a look at an example so you can kind of see what I mean. So what we'll do is we'll come down and we will look at this. We are given p of 7 pi over 6. So that is the notation I just showed above where we have p of theta. And let's start with a reference angle for this. So where will 7 pi over 6 be? It's a little bit more than pi. So it will be down here in quadrant 3 with a point on the unit circle. Let's draw in a triangle and label our reference angle. Our reference angle is this little piece in here. So if the entire angle was 7 pi over 6, what is our reference angle? It's just pi over 6. So we have a right angle, we have a reference angle of pi over 6. Our radius is 1 because this is the unit circle. And if we go back and look at our special triangle, find that place where you had an angle of pi over 6. Your opposite is going to be 1/2. Your adjacent is going to be root 3 over 2. So let's just draw those in. Our opposite is 1/2. Notice we are in quadrant 3, so this is negative. And our adjacent, or our x value, is root 3 over 2. And this one is also negative because we're on the negative x-axis there. So we have an x value, a y value, and an r value just by drawing our special triangle for that angle. So if we are asked to find the point on the terminal arm P, we can write P x comma y, but we just found our x value and y value using the triangle. So we would just write P. For our x value, we'll put in negative root 3 over 2, comma, negative 1 over 2. If you did the same steps, but you did not use the scaled down special triangle and you used the original special triangle, you would get a point on the terminal arm, but it would be on a larger circle instead of the unit circle. So because we are specifically talking about the unit circle with a radius of 1, we just need to scale down our triangle a little bit. Let's do another example of that. So this one we'll do negative pi over 4. So this is our format P of theta. Our angle is negative pi over 4. Our reference angle is just pi over 4. This is negative, so we will go in the negative direction. And we'll have our point P there. That is P of negative pi over 4. Now, because our reference angle is pi over 4, again, we want to pick a special triangle. Let's go back to our special triangles and find one with an angle of pi over 4. We can see that our side lengths, are root 2 over 2, and our radius is 1. So let's put those same side lengths on our triangle, and we just need to check the signs for x and y. So this will be positive root 2 over 2. This will be negative root 2 over 2. This will be 1. A point on the unit circle that is on the terminal arm of that angle is root 2 over 2 for x, comma, negative root 2 over 2 for y. So actually finding the point is very easy, but our steps are draw your angle in standard position, find a reference angle, and then use a special triangle. And let's do one where we go in the other direction. So for this one, we are given the point with an x value and a y value, and we want to find the angle theta. So let's start with just drawing the point. Notice that we have a negative value for x and a positive value for y, so it looks like we are up in quadrant 2. And let's draw in our triangle with our x and y values. There's our angle. So note that this is actually our angle, but we do have a reference angle, theta r, in there. And radius of 1. We are given here our x and y values, so let's put those in for x and y. So x is negative root 2 over 2, y is root 2 over 2. And we're now at the point where you hopefully look at those side lengths and recognize, oh, I know a special triangle like that. That reference angle must be pi over 4. Do you remember it was our reference angle in the last one too? So our reference angle is pi over 4, but we want to find the angle in standard position in quadrant 2 because that's where our point is. In quadrant 2, keep in mind that this entire angle up to here would be pi. So if we do pi minus our reference angle, we can get the actual angle. So theta is going to be equal to pi minus pi over 4. So you can think of that as 1 whole pi minus 1/4 of a pi. And our angle is 3 pi over 4, or 3/4 of pi. And that's really just the basic idea behind what we're doing. So we may start with an angle and be able to find a point on the unit circle. We may start with a point on the unit circle and be able to find an angle. Right now, using the focus that we are sticking with special angles that we know a special triangle for.